Starting out with the example binning data. Example is binning data. So you can use these ideas to efficiently bin data to create a histogram by hand. For example, imagine we have 1,000 values and would like to quickly find where they fall within an array of bins. We could compute it using ufunc.add like this. Starting it off with np.random.seed42 x is equals to np random now compute histogram by hand bins equals to np dot linspace minus 520 counts is equals to np dot zeros like bins find the appropriate bin for each x. I is equals to np dot search sorted odd one to each of these bins. np dot add counts 1. Now the counts now reflect the number of points within each bin. In other words, a histogram will plot the results. Plot bins counts line style steps. This would create a histogram, hand 1. Okay, so here it is. So of course it would be silly to have to do each time you want to plot a histogram. This is why matplotlib provides the plt.hist routine, which does the same in a single line, like this. JST type step. So this function will create a nearly identical plot to the one seen here. To compute the binning, matplotlib uses the np.histogram function, which does a very similar computation to what we did before. Let's compare the two here, starting off with print numpy routine. Time it, counts, edges, 3 dot. Now print custom routine np dot counts np dot bins so now it will compute the routine. Yes, we got the result. So our own one-line algorithm is several times faster than the optimized algorithm in Numpy. How can this be? If you dig into the np.histogram source code, you can do this in IPython by typing np.histogram double question mark. You'll see that it is quite a bit more involved than the simple search and count that we have done. This is because NumPy's algorithm is more flexible and particularly is designed for better performance when the number of data points become large. So now let's continue our coding further. X is equals to np dot random print time it counts edges dot histogram then print time it np dot add counts np dot search sorted bins. Now we'll get the result again. So with this comparison shows is that algorithmic efficiency is almost never a simple question. An algorithm efficient for large datasets will not always be the best choice for small datasets and vice versa. But the advantage of coding this algorithm yourself is that with an understanding of these basic methods, you could use these building blocks to extend this to do some very interesting custom behaviors. The key to efficiently using Python in data-intensive applications is knowing about general convenience routines like np.histogram and when they are appropriate, but also knowing how to make use of a lower level functionality when you need more pointed behavior. So now, let's move on to another topic, which is sorting arrays.